All right. Last time we were talking about building an LO1 table. And from that LO1 table, being able to mimic the LL parsing process. So we got a couple examples of that, but where we ended was looking at grammars that aren't LL1 and either might be LLK or might not be LLK for any K. So the question is, how long of a look ahead do we need in this grammar to be able to distinguish between the different productions going from non-terminals to their right-hand sides? So Nathan says he thinks the answer is 4.
I think I'm probably wrong, and I'm probably going to kick myself once I see it.
But how would we figure this out? We need to go from non-terminal to non-terminal. So looking at every single non-terminal, figuring out, okay, how much of a look ahead do we need to be able to resolve ambiguity in this look ahead? So the easiest one to do is C. So we're going to start with C. We see both left-hand sides start with both right-hand sides to C start with A. So we cannot use a single look ahead to determine whether we want to be the left-hand side or the right-hand side. But if we use a 2-character look ahead, the first production is AB, the second production is $. The only way to do this is to get the end of string marker at the end of that C, because the C in the S production has to end the string. There's no other way to get back to S. So AB and $. Are the only possibilities for what we could see as an expansion of C. So because of this, a 2-character look ahead could resolve C. Unfortunately, that's not the answer. We need to look at every other non-terminal as well. For B, both of the right-hand side start with a different terminal character. So a look ahead of 1 is good enough. But for S, here's where the fun begins. So the real question is, what is the longest string that we can make that shares in common between these productions? So the guess on hand, the educated guess is 4. Let's see if we can do this. So we need 2 different derivations starting with S, one of which uses the leftmost right-hand side, one of which uses the rightmost right-hand side. We're going to attempt to make these the same for as long as possible. So this has a second A. What do we do to this to make it have a second A? Replace the B with AB, has to be. So we have the A followed by an AB. All right, what can we do next? We know that anything that this C generates has to generate an A. Is there an intelligent way to make it generate enough characters that we can do this? We probably want to take the ABC over the A. So let's do that. We have A, B, C, and then we can map this third A with this AB by replacing the B with the AB again. So we take A, B, and now we need to generate a B here. And that maps this B to that B. And now there's no way for this C to generate this C. So this is kind of the breaking point there and there. We shared the first 4 characters in common. So does that give us, what value of K is this for LLK? It is 5. We need the 5th character in order to distinguish it. So 4 characters in common. But when we find that 5th character in a look ahead, we know we can backtrack all of this to say, on that 5th character, this isn't a C, this goes to something, either A, B, C, or A, which is not a C regardless. So this is going to be an A. But on that 5th character, we can backtrack to determine which S production to apply, which is what we care about. This whole process up to 4 characters could be ambiguous. Once we get that fifth character, we can distinguish between using AB and AAC back all the way at this S. But that is the longest such string that they could share in common. So that is the maximum size look ahead that we need to consider. Questions on that? How much sense does it make?
At least like intuitively, like I don't think I'll be able to write an LL parser based off of this, but like that makes sense.
Yeah,
So you try to build the longest possible identical strings out of different derivations and until they are forced to be like differentiated and they're like, okay, that's K. K is that plus one.
yeah. So if we look back at the LL1 table that we made last time, instead of making a character sequence that is based on one character, we would have to make every combination of 5 characters in an LL table in order to be able to remove any possible ambiguity in the table and be able to parse it efficiently, which is kind of gross. There are a lot of combinations of 5 characters. Good question for us all. How
Wait.
many of them are there?
So that's like the number of characters in the alphabet raised to.
It's close. Because we also have to include dollar, the end of string marker.
Okay.
Which, so yeah, we would have all 5s in a row. So we would have A up to a dollar. Same with the B's. So there are 1, 2, 3, 4 of those. There'd be 4 of those. There'd be 4 of them ending with B. So we have now we have 5 characters raised to the 4 to be able to do that in any given order. But then we also have to consider what can end with the 4th string being dollar, because dollar is the end of string marker and nothing can come after that. So we need all sequences of 4 that must end in dollar. So that's combinations of 3 followed by the dollar at the end. So that's 4 to the 3rd. Then we need all the places where the dollar comes 3rd, which is 4 squared. Then where dollar comes in the 2nd position, there are 4 of those. And then 1 where dollar comes in the 1st position. So we would end up with, I guess we can't have 4 as the base. We need 4 to the 4th. It's not 4, it's going to be 3.
Yeah.
Yeah, and then we need to consider the dollar $7. 3 to the 4th, that gives, as we take 3 to the 5th. Because that gives us all of these arrangements without the dollar. Plus,
3 to the 4th, which is all of the.
yeah, 3 to the 4th, which gives us everything where we hold the dollar constant at the end. Plus 3 to the 3rd, holds the dollar there, plus 3 squared, plus 3 plus 1.
We love combinatorics.
Is there an easy way to represent this as more than just this long sequence?
3 to the 8th. That's 3 to the 6th.
Times 5 over 2. Or 5 times 4 over 2. Remember that Gaussian.
Yep.
Sumness.
So we see that as we do this, we're doing something in terms of 3 to the 6th, which is super useful. Fun. So it gives you a sense of the scale of how quickly this can blow up for LL values that aren't 1. So we mostly care about LL values that are 1 or 2, but as soon as it scales past that, we're going to end up with an exponentially scaling number of columns in our LL table. which very quickly becomes annoying and unfeasible to think about in person, and reasonably quickly becomes infeasible for computers. Yes, this is an LL5 grammar. Last example I have for you. LLK for which value of K?
I know I said this last time, but this one has to be to the end of the string. For real this time, I swear.
What makes you say that?
Because you can do an infinite loop of A's really easily,
Yes.
and you don't know whether you chose the first option, which is capital A B, or the second option, which is lowercase a capital A C, until you get to the end, because it's the very last character.
Right.
So you can't tell which derivation you've chosen until you see the whole thing.
I second.
Okay. I'm not going
And there could be ambiguity within that that says that you could generate it either way.
also real.
Yeah, for A, first two productions can both generate an infinite number of A's. And what this is gonna say, the result of this is not, it's the end of the string, it's that there is no value of K that will be able to distinguish this, because we don't know how long the string is. The string could be arbitrarily long, but there is no look-ahead length that guarantees that we can pick between these two productions.
I see.
So it's the absolute correct logic, but the conclusion that you want to derive is that this is LLK for no value of K. It's not LLK for any value.
Okay.
Yeah, so excellent job figuring that out.
And this is the case in which we use CYK because there's no other option.
Yeah.
Okay,
And you have to convert this into Chomsky normal form before you do that,
fair.
to be sure, but every context-free grammar can be converted into that. And you would be able to do this for CYK. But yes, this is an example of a grammar where there is no hope to do this more efficiently than CYK. Any questions on LL or doing this before we jump into question?
When we're doing our first projections. Could first of lambda be what, $1?
You don't really define first of lambda.
No,
You add lambda to first of A.
but aren't we recursively like? First of A is equal to first of AA. First,
Yeah, so A would be involved in first of A. And that would be it. You add lambda to it, so wherever A shows up, you may have to go past it. So
And that's-
first of A could be B or C because of where it appears in the,
right. So that really gets into like the follow tables then. doesn't it?
yeah. Yeah, first of A is still just A, but it's A and lambda, so when you calculate the follow, you know to derive that lambda that the A's in the S productions could go to lambda, so we need to consider the next character.
So S could have first be because it is lambda.
Yeah. Anything else? Other questions? These are all good. All right, we're on to the last slide deck that I have prepared for this class. It's crazy how that's happened so quickly,
Awesome.
which means that plan starting next week is going to involved, so we'll get through this. This might actually take a couple days because it's one of the more complicated things we've done in the class. But I plan to at least have a class period or two where we can work on our last project, which is implementing LL parsing. I want to have a day maybe that it's kind of like an extended office hours where people are working on homework or ask questions about homework, and that way for those who have a bit more difficulty making it to my office hours can get the same level of assistance with assignments. And then I also just want to cover other random things that people might be curious about that you never got a chance to take a course in or don't know if you'll be able to take a course in. That is something else that I have prepared. This could be talking about things like interviewing in positions. This could be something like talking about AI and machine learning. Whatever people are interested in. We can also go back to some of the optional topics in compilers and talk about some of those as well. But I want to make the last couple of weeks actually useful to you, rather than just say, oh no, we ran out of content. I don't have time to make a ton more content. And this is kind of, in 10 weeks, this is really a natural stopping point after we talk about LR parsing. To dive into more detail than that would be to have you start building a compiler via all the components that we talked about.
Yeah. Let's do it.
Yeah, let's make a lecture. We can make a lecture.
This is our chance.
We can make a third project that we have to do.
Yeah, I know.
Make the perfect programming language.
Such a thing does not exist. So I guess we could kind of talk about programming paradigms, language paradigms as well. Have you read a quick program in OCaml?
Okay.
OCaml, my camel. It's a fun language.
But not white space?
No, that has no use. Functional programming languages have a use. All right, well, let's talk about LR parsing, because LR parsing is really cool, but at the same time, it's reasonably complicated. So we found that sometimes there were grammars that weren't LLK for any K, and I had moments ago said that the only hope is CYK. That's not actually true. It could be that there is a grammar that is not LLK for any K that is actually LR of some K. And so the intermediate step is to look at a bottom-up parsing process that may be able to solve the grammar more efficiently. And only if you have something that is not LL of K and LR of K for any K, then you're screwed. But yes. So yes, LR grammars are more complicated than LL grammars, but there are more grammars that are LR grammars than are LL grammars. So that's kind of your trade-off, a little bit of extra complexity, but we group a few more of the grammars into that bubble that allows us to do that. So just like we did before with converting a context-free grammar to an NPDA that mimicked the LL parsing process, we're going to do exactly the same thing for an LR parsing process. So how could we convert this in a way that mimics this instead? So just as before, we only have these three states. We have an initial state, we have a middle state where all the work is being done, and then we have a final state that we transition to once we are done. But unlike, I kind of lied to you, unlike the LL parsing, Q0 is where most of the transitions are going to occur instead of Q1. So for each production in the grammar, we have some non-terminal to a sequence of terminals or non-terminals that we're going to call X1 up to Xn. And we need the associated transition rules. We are now going to be, instead of looking at single characters, we're going to be pushing and popping strings to the stack, which is very strange to think about. So no single characters, our stack is a string stack now. It's going to push strings. So the associated transition rule is going to say, from Q0, we are not going to read past any character in the input, and we are going to pop the entire sequence of non-terminals that is on the right-hand side of each of these productions, not each, but some production, whatever is on top of the stack. And then we are going to stay in Q0 and push the left-hand side of that transition. Which is what you would expect in a bottom-up parsing process. We're replacing a right-hand side with a left-hand side. So we are going to be popping off a string that represents the right-hand side and replacing it with a character that it represents the left-hand side of the grammar production. This is called a reduction. When we go from the characters of a right-hand side to the character that's the left-hand side, we're taking a lot of characters, converting that into a single character. We call that a reduction. And then we need some more that we're going to call shifts. For every terminal and each stack symbol, we now need the ability to shift those. So every transition rule like this, we're going to have from Q0 on a terminal, we're going to pop a stack symbol. This is for each stack symbol. Then the destination for that is we stay in Q0, and then we concatenate the terminal and the stack symbol. And this is a shift. So this is the concatenation rule where we see a new terminal, we're going to put that terminal on top of the stack. And then 2 more transitions to complete. How do we get from Q0 to Q1 and Q1 to Q2? From Q0 to Q1, we need to identify and remove S on top of the stack. And then to move from Q1 to Q2, the stack must be empty. Which means that beneath that S, there can't have been more stuff. That tells us that it was the last S, that we managed to get the entirety of the string reduced down into an S. And as usual with this, it makes way more sense after going through an example. Any questions on the terminology in here before we get to that example?
This shifting or the second major
Yeah.
point. That means you're seeing your look ahead character, you're adding it to the string that you're currently looking at.
Yeah, so there's every possible transition rule because this is non-deterministic. So yeah, we need the ability to concatenate every possible terminal symbol to every possible stack sequence.
So say my current string is like AB, my look ahead is C, but I have no production. That maps to that?
Not quite. Let's give you the example. I think that the example will clear this up in a better way than I can explain it before talking about the example. But if it's not clear after the example, make sure we come back to it. All right, so let's give you the example. So we start with 3 states. Here's our grammar. We are going to add the reduction transition rules. So this is again saying for every left-hand side, replace it with a right-hand side. So from Q0, we always have lambda as the second. We're never reading past anything in the string. We're going to replace a right-hand side with a left-hand side for every right-hand side to left-hand side pair. The shift transition rules have us going through and saying we can read an A in the string. And when we see A at the beginning of the string, this allows us to kind of take that. So for every possible X that could be there, we're going to pop A at the front of it with that X, shift past the A, and what's left is the X.
So we're narrowing our scope.
Yes. Yeah, we're not adding to the end, but we are removing the first character of when you have a terminal, and that terminal happens to be at the start of the string. But note that X, of course, can be terminal, non-terminal, or Z. Then we have the final transition rules. And we get something that looks kind of like this. And again, these X's are for all possible X in the associated grammar. So for all X in the terminals union, the non-terminals union C. So even more transitions than we had in the LL model. But it turns out to build an LR, we need some additional ideas as well. So what's the process? We shift symbols from the string onto the stack. When appropriate, we pop a right-hand side off the stack and replace it with a left-hand side, doing a reduction, but we're gonna have to guess between sometimes when a shift is necessary and when a reduction is necessary, because sometimes you can have both. So yeah, this is non-deterministic. Determining shift or reduce happens in parallel with non-determinism, and LR is going to make it where we know exactly what to do here. So we need that additional information to turn this non-deterministic problem into a deterministic one, because non-determinism is never useful to us in practice. So if we want to do this in practice, we need some way to turn this into some deterministic process where we can actually choose between a shift and a reduce. So we're again going to store a look ahead. But now instead of a look ahead of our arbitrary length, 1 character, 2 characters, 3 characters based on the K and the LL, we are instead going to only care about the next character in the string. And so there's really only an LR1. So we're going to use the same grammar as we did before, the same string ABCAB. We're going to trace it using a look ahead of 1 symbol. And just like before, let's go ahead and take a look at exactly what happened. So take a look at this for a moment. And let's see what happened. The look ahead tells us what the next character is. So what we are going to do is shift onto the string, onto the stack, unless there is a possible reduce, in which case we have to choose between shifting on the next character onto the stack, or taking what's on the stack and reducing it by replacing some right-hand side of a production with a left-hand side of a production. So there's no right-hand side that is a Z. In fact, Z is not a legal character in this grammar, so we must shift on the A. Is there any right-hand side that is an A? No, so we must shift on the B. Is there a right-hand side that is a B or an AB? No, so we have to shift on the C. But now there is a right-hand side that is a C, so there is an ambiguity between whether we shift on the A, that is the 4th character in the string, or whether we do a reduce, changing that C into its left-hand side, which is an A. It turns out that to make this process work, we need to do a reduce there, not a shift. So we replace the C with an A, and then what's on top of the stack is another reduce. I guess maybe we did a shift before that. So we shift on the next A, and then there's the B capital A that is the right-hand side of an A. So we do a reduce again. That A can reduce into an S. Then we have a final shift, getting the last character on the B. Then we reduce the ASB down into S. Then we can move ahead to Q1, removing the S, and then move into the accepting state Q2, because all that's left on the stack at that point is the bottom of stack character. Does this make sense?
Kinda.
So we always have the option to shift onto the stack the next character. And if somehow what's on the stack, buried to some depth level, is the right-hand side of a production, then we can replace the right-hand side with the associated left-hand side. And if at some point all that's left from that is an S, this is how we go to Q1 to get rid of the S, and to Q2. If the look ahead is dollar and this is empty, then we know that we can accept. But there were multiple steps where we need to determine between a shift and a reduce. Like here, we could have shifted on the next character, this A, but instead we chose to reduce. So that's where the non-determinism is coming from. And similarly here, we could have shifted instead of a reduce, because there's still another character to come. So we could have put a B on top of this, but instead we non-deterministically chose to reduce. Same here, we could have shifted on this B, but instead we non-deterministically chose to reduce. You can see that if you make the wrong choice, then you don't accept, but this is the path that is possible with this. So there were other paths that we could have taken, but because a single path does lead to acceptance, then we accept the whole thing non-deterministically. However, what we haven't done is show how to turn this into a deterministic process. So that's the next step, is to say, there was non-determinism built into this. How do we resolve that non-determinism and turn this into a deterministic process so we can actually use it?
Any guesses on the lookup table?
It ends up being more complicated than a lookup table.
Uh,
We actually need to define some new concepts. And it turns into one of the coolest things we see in the class, which is why I go over it. So there's actually going to be no homework or no exam questions on LR parsing, just because it's a little outside of the scope. But I think it's very fun to look at, because it actually, we're gonna build a DFA as part of this. And that DFA is going to solve this problem deterministically for us. But to do so, we need a couple more definitions. But any questions on the steps of going through this process before we go do that?
I kind of thought like, well, can't you like define your grammar in such a way that like it will just automatically work if you just greedily reduce, like if you reduce whenever possible?
To do that, we would have to have stored every possible look ahead or
Yeah.
deep down into the stack, because you can only peek at the top character. So we need to know how far down that reduce is. Because like in this case, we reduced 3 characters down to 1 character down, which would require us to know, can we reduce from this character? Can we reduce from these characters? Can we reduce from these characters? Can we reduce from these characters?
Mhm.
And that's going to store more and more and more information the longer the stack is. And there's still the option between shifting and reducing at any of those levels. What if you could reduce multiple possible places?
I was gonna say, what if you did like a bejeweled combo?
Yeah. That's a great way
That's
to put it.
great.
I can't wait. For about 50 years from now, there are going to be so many technical terms that were derived from right
From modern slang.
from modern slang. Yeah,
Like meme language.
yeah.
Yeah.
I can't wait for that to infiltrate academia.
This algorithm is a cooked of n algorithm.
No, I think it should be a Candy Crush. But wait, what? Oh no, that's just the new term for a greedy algorithm. All right, so the two terms we need to define are items and closure. So we are first going to define what an item is. So we do need to know when we have the right-hand side on top of a stack. That's really hard to do without digging down into the stack. By the time we push something onto the stack or pop something off the stack, we need to already have stored somehow whether there is a possible reduce. But because we shift everything onto the stack one at a time, we actually have the ability to do this. So we need to keep track of which symbols are on the stack and which aren't, which means that we're going to add a marker to every right-hand side of a production that says, here is how much of this production is currently on top of the stack. Those markers within that string are called items. So given a context-free grammar, an item, or you can think of it as a marked production, is a production with some marker in it that delineates everything to the left of this is on top of the stack in that order, and everything to the right is not yet on the stack. So the idea is when that marker is all the way on the right-hand side of a production, then we can reduce that production.
That's inclusive, right? So if my character is on the far right, as you said,
Yeah.
that character is also on the stack, or is it that everything?
It's not actually, the marker is never on the stack. But
in
when you're,
in the sequence.
Yeah.
But
yeah, so if we have a right-hand side like ASB and the marker is all the way on the right, then we know the top 3 characters are B, capital S, and A in that order, so that we could make that reduce. if the marker is after the S, then we know the top two characters of the stack are S and A. And if we see the next character, if we can shift on a B, then the marker would move to the far right, and then we could reduce. So yes, marker can appear anywhere in the production, including the very beginning, but it's always between two characters. It's never at a character, always between, before the first character, after the last character, or between two characters. So n+1 possible positions if there are n symbols on a right-hand side, makes sense. If there is the first symbol that is after that marker, if it is a terminal, then we look at the look ahead and determine if we can shift on that terminal. That is what could move the marker one space to the right. If it is a non-terminal, then what we're looking for is a reduce to that non-terminal as a way of now moving that marker forward past that non-terminal. So could we build up some sequence that reduces down to the non-terminal so that we can move forward in that? Maybe that doesn't make sense. There's a lot to this. Let's say we have that. Something very simple. So on our stack, because this is the marker that's saying we have this here, it would also technically be here. We have A on the stack. And if we wanted to move the marker past this S, we would need some way of now producing that S in some capacity. So actually, I'm going to not make this an A, because then I don't want the marker either. Let's say this is a B. We have, in order to move this past this S, what happens if we were to now shift on a B? If we shift on a B, then the marker would be from here, this marker would go to here, and say, now we can reduce this B to an S. When we reduce this to an S, we can now move this marker past here, with that S being on the stack. So you have to find a way to reduce to that non-terminal so that when you reduce it to it, now we can move the marker past that non-terminal. Let's see. There's no other way to just have an S. You can't shift a non-terminal onto the stack, so you have to reduce into it.
Is it possible with like more complex languages where there's like multiple derivations to still have a DFA where it can?
Yep.
Okay.
We'll show what that DFA looks like because it gets really complicated pretty quickly. But once we see it, I think it becomes really cool. So yeah, to be able to move the marker right one symbol, we either need it to be a terminal and to shift it on, or we need it to be a non-terminal. We need to reduce into that non-terminal so that we can move the marker to the right. And as that marker moves to the right, the whole goal of that is to be able to reduce that. So you can see how this is recursively defined, that we need to make some other reductions that we can move forward with the hope of reducing this. But that's the whole point of a bottom-up parse, is that we are reducing and reducing and reducing all the way down to an S. So in order to build the next step of the large scale reduce, we might have to have a sub-problem that is some smaller reduce. All right, those are items. Let's talk about closure. Given a context-free grammar, the closure of W and B is a set of items defined as follows. We initialize the set to contain a single element, A arrow W dot B, where the dot is the marker in an item. Loop the following until we add no more items to the set. For every production in the set, if there's a dot before the non-terminal, add a new production to the set, B arrow dot the entire right-hand side for each possible right-hand side, assuming that that non-terminal is a B. And that's the entire process. You just continue to loop that for each production that exists in the set, the dot is before a non-terminal. We're gonna start saying, what are all the symbols that we would need to reduce into that non-terminal so we could so we could move the marker past that. As always, makes more sense with an example. So what is the closure of S arrow A dot SB with this grammar? And so we start with, too many things at once, start by setting the closure equal to itself. And now we can say, let's loop, and for every possible S right-hand side, because this is the non-terminal, but this is right before, we want to say, what are all of the elements that could reduce into this such that we could move this dot past this? And that would say, to do this, we need to see either this production or this production of some kind. So we're going to add both of these as elements of our closure, where the marker is at the far left-hand side of these, because we haven't seen them yet. But if we do see them, then we could reduce down into the S, where we could move the marker past the S. So that adds both of those productions as elements in this set, where the marker is placed at the far left position. And now if we see this, if we are able to see all of this, this could reduce down to the S that we need to move past here. If we could find this, reduce into an A, then we could move past the A, which can reduce to the S, so we can move past the S. How are we doing? To what extent does that make sense?
The concept makes sense. I'm just trying to figure out how you could even like design a DFA for this that doesn't use non-determinism. So like,
I will have to show it to you.
Yeah.
It's reasonably complicated. I mentioned it was a little bit more complicated than LL. It's a lot more complicated than LL.
I didn't think about like, well, how you solve the problem using a stack in this case if you don't know the context, just use a DFA. It's like, oh, it's just Inception. You have like 7 sets at this point.
What's crazy is that someone thought of this, and it's useful for parsing grammars effectively in the construction of a compiler. So cool. So yeah, last element of the set now to the left of a new non-terminal. So now we have to add both A productions to this as well. That says if we could move past the A, then in order to move past the A, we have to see the elements of that A. So this closure says, what are all of the ways that we could move this marker past this S? And to move this marker past the S, we could reduce down to the point where we could move past an S, great. And the way to get to that is either from here or here. But recursively, in order to move past this A, we have to see an A. So here are all the ways that we could see symbols that reduce to an A, so we can move past this A, so we can reduce to an S, so we can move past this S.
The closure of S always gonna be this all items, all productions.
The closure is always for a left-hand side arrow or the right-hand side with a marker placed somewhere on that right-hand side. And the only ones we care about are those that are where the marker is right before a non-terminal. Because if it's right before a terminal, then the only thing that can move past it is a shift.
But it's always gonna like, because this is the S, it's our start terminal, is it always gonna end up branching to the entire?
No.
No.
Only if, so we added something that was right before a non-terminal because of that production. So we had to recursively now say, well, what allows us to move past this A is every definition of the A as well. So yeah, it was recursively defined. But now every single element in here, either it's before a non-terminal where every right-hand side of that non-terminal is there, or terminal, thing we defined, terminal, thing we defined, we're good. So as long as you're adding new things that are at the left-hand side of a non-terminal, we need to recursively add all right-hand sides of that non-terminal to this closure. But this closure now allows us to say, these are all of the possible ways to move this marker past the S. All of that information is embedded in this closure. So yeah, no more new elements were added that were to the left of a new non-terminal. So we are done. And we will find that this, both the items and the closure are necessary as we do this. So what do we do? So we'll start by saying, suppose there's a marker to the left of an S in this item, which means A is on the stack. S and B are not yet on the stack, but if they could be, if we could find a way to manipulate this string and the stack such that the S and the B were on the stack, then we could reduce to an S. So we know that a shift operation placed the A on the stack. To get S on the stack, we have to reduce to an S, meaning all symbols on the right-hand side of some S arrow right-hand side have to be put on the stack before we can move past that S. Everything on the stack for some element of its closure. Once we do that, on the right-hand side reduces to S and we can move past that S. Once we do that, then this marker moves past the S. So here's the algorithm. But we do need the ability to look multiple positions down the stack. But we can build a DFA that allows us to look those multiple positions down the stack, where each state in transition allow us to move between the elements of the items and closures that tell us everything that we need to do. So for each state of the DFA, we're going to associate a set of items from the grammar with that state that tell us when we're in this state, here are the elements that are on the stack and need to be on the stack, which have yet to be added. When we parse a string, we trace through the DFA. And then there's a final state. If we get to a final state, it indicates that the right-hand side is on top of the stack, and we can now do a reduce. And if we keep track of a history of which states we visited, then we can backtrack the arrows of what we did to say, this is what put this on the stack, this is what put this on the stack, this is what put this on the stack, and that becomes our reduce. So going forward are our shifts, and going backwards are our reduces in that DFA. Let's give you an example. I have no hope that this is going to be something that I can give people and is going to happen, so I'm just going to go through it. So we add a new start symbol and a new production, S prime arrow S, as just something that you always do. Then we can number the productions as such. There are 5 of them, with the 0th one being that new S prime arrow S. Create a start state, Q0. And we start by calculating the closure of S prime arrow S. And there we have it. We associate this set with the state Q0. And there we have Q0 with this box of information that are all of the possible items that relate to Q0.
That's what the setting and J flap is for. I see.
Fine, it makes sense now.
It does.
Next, we're going to expand state 0. Each of these 5 elements are associated with a state that creates a transition out of state 0. So for S prime arrow S, we move the marker over the S to create the new item, S prime arrow S dot. Closure of this adds nothing because there's no non-terminal to the right of it. So we make a new state Q1 and associate just this item with it. For S arrow ASB, move the marker over the A dot SB, and we define the closure of that. So that adds some more things. We create state Q2 and associate the new set with that closure to that state. And we just continue to loop this process for the 3 remaining states, and we get a partially completed DFA. And I'll come back and explain how this becomes the actual full completed DFA on Monday. And we'll actually walk through this for an example and show you how we can do an LR parse with this DFA. If
Is
you gotta
this-
go into a next class or something, feel free, we are out of time, but I will stay and answer questions. because
This is a DFA, so there's one DFA like this for each production rule, right? Or is this for the whole?
This is for the
grammar?
whole thing.
This is the whole grammar.
Yep,
Wow, dang.
yeah. So at this point, we actually can start in Q0 and you see that we can shift moving forward and reduce moving backward. And if we reduce into a non-terminal, then we can move past that non-terminal as
Okay.
such.
Okay,
Then we can move back and move forward past that in ways that say, we can now replace this A with an S, where we can now move backwards and move past the S, wherever the S comes from.
Yeah, so you basically just answered my question. Every single final state on this is a reduction.
Yes,
That
yeah, you've produced the point where you're at the far right-hand side of something. So we can now go backwards from the B, backwards from the S label, backwards from the A label. And that reduces these things down to the S, where we can now shift and move past the S to the next thing. And once we move past the S prime arrow S dot, this is the true final state that says that
Right.
that we accept.
and so, yeah, and so this DFA, obviously, it isn't doing the stack manipulations, but whatever's manipulating the stack is checking the final state to determine what it's gonna do.
Yeah.
Interesting.
So this all mimics what an NPDA would do, but it's a DFA. So that we can use it to determine the membership question.
Yeah.
And this works for more grammars than the LL process does. It's just a bit more complicated and
is,
requires a lot more memory because these explode fairly quickly in reasonably sized grammars.
so what's the restriction on the LR parsing? Is there like certain strings that it also can't parse and we still have to go to CYK?
Yep.
Are we gonna talk about that tomorrow or Monday or?
There are only a couple slides left in the class. It's hard to determine exactly the rule set for what can be parsed with LR and what can't. It's just that LR is a larger set of possibilities.
Is there still like a process that we can take like with the LL parsing where it can just be like, well, we can't do this because
You'll find an error in this construction
Okay,
or a loop in this construction
got it. Interesting.
where the DFA becomes larger and larger and larger and larger and larger. So you need kind of the equivalent of a pumping lemma. Be able to say no such DFA could exist that could model the LR parsing process.
Yeah.
Interesting.
Please, God, let there not be such a thing as the LR parsing DFA pumping lemma.
I'm just waiting for the recursion of the pumping lemma.
Yeah. Oh, no.